First of all, Team 22 would like to thank all of you for taking the time to watch our presentation and listen to the design for our 30-pound combat robot, Thunderstrike. I'm Jordan Bergal. This is Brandon Augustus, Catherine Byers, Harry Rodriguez, Ken Sabak, and Kyle Stevens. So the objective for this project is to meet the requirements for, compete in, and win the second annual Bengal Bot Brawl hosted by LSU, and by doing so advance to the MomoCon Robot Battles Championship in Atlanta, Georgia next May. We identified our customers by customers that we could clearly identify their wants so that could drive our project. Our two primary customers are the competition judges, who are going to determine whether or not we qualify and whether or not we win matches, and the Capstone Design Team 22 ourselves, because we have the biggest investment in this and we want to succeed and win in these championships. Our secondary customers are the competition audience, who's come to see a good time, as well as the LSU College of Engineering, who we're going to be representing at these competitions. We identified three main robots as existing technology that we could base our success on. The first is Nyx, who's possibly the best combat robot in these featherweight championships. It's a modular design that has either a pneumatic pincher, an axe, or a pneumatic or electronic lifter. Favors using the electronic lifter and has over a 70% win ratio in these matches. The second is Pushy Grabber, who has twin rotating cylindrical arms that are able to upend opponents, remove their pushing force, and push them off of the combat arena. And the last one is Goliath, who actually won the LSU Bengal Bot Brawl last year with a very effective flipping mechanism, which could also self-right itself. So there are a lot of functions that a combat robot needs to be able to perform. Ours specifically is portrayed in this objective tree. The four main objectives are attacking, defending, communicating, and moving effectively. Attacking in our case is going to involve activating dual pistons for our weapon, as well as overpowering enemy traction so they leave the stage and not us. Defending is both explicit and implicit. We need to protect our internal components, but we also need to be able to avoid or counter enemy attacks. Communication is done with our electrical system, and we need it not only to control a robot, but to shut it off in the case of an emergency. And then we need to be able to move effectively in the arena, as well as maintain traction at all times.
These are the qualitative constraints that we set at the beginning of this semester for our robot. We wanted it to be easily transportable by hand. It's only 30 pounds. That's, not that big of a robot, and it needs to not have any sharp edges or be overly bulky. We obviously need it to be durable because we're going to be probably sustaining attacks from enemies and falling off the stage. So it needs to be able to take a few falls and not suffer catastrophic damages. It obviously needs to operate wirelessly and not need physical assistance when it's in combat. So can't go in there and help it. It obviously needs to also be safe for any onlookers, us, the judges, the audience, and make sure it doesn't do anything that might endanger them in any way. And in the case that we do sustain damage, it needs to be easily and quickly repairable on the sidelines in between matches. These are our measurable engineering specifications. We obviously have several, but what's important to us is mainly the weight. We have a limit of 30 pounds plus or minus 2.5%. If we go over that, we're disqualified. We have a budget, obviously we had to follow. We, our max speed, or our average speed was 7.5 feet per second was our target value, and we didn't want to have our max speed go very much over that because we thought that would be hard to control in a 16-foot by 16-foot arena if we went any faster than that. And several other specifications here, such as our hull strength, our traction, our motor power will be examined later on in this presentation.
This is our concept generation process. During phase one, each member of the team individually created multiple concepts that we came together as a group to discuss anonymously. We based these discussions around feasibility, offense, defense, and ingenuity. During phase two, we picked the top three choices from phase one and rank them in a better decision matrix. And from there, we made a selection. On that selection, we decided to talk about the subsystems of the robot in order to improve the certain concept design we selected. This is one of our top 3 concepts from phase one. It's the tank pusher. It uses tank treads to gain extra traction on the stage when fighting other opponents. When flipped over, it's able to operate on the other side as well, so that is an advantage as well. It has pneumatic pistons to attack opponents as well. This is our push to lifter design. It's able to flip opponents and push them off. So and it's able, with the flipper design, is able to self-right itself and design itself. So we have that, and it's very maneuverable, very able to maneuver really easily. This is our red stabber. This design is very orientated towards defense. It's very low to the ground, so it won't be able to be easily flipped over. It has a slanted side, so no attack can be directly onto the shell of the combat robot. And then it has a stabber to know to pierce opponents. And this is a decision matrix for our concept selection for the top 2 choices. It's based on durability, defense, offense, maneuverability, complexity, and manufacturability. The weights scale from 1 to 5, 5 being the highest weight, and performance values of -2 to 2, 2 doing very well. And these legends here would be used for the rest of the decision matrices in presentation.
This is an exploded view of our robot. The main purpose of this image is to show the main components and where they'll be placed and how they'll be constructed. This is the internal architecture. We have 2 batteries. One will be powering the motor, which will be controlled by the speed controller. The other will be powering the pneumatic system. And as you can see, the pneumatic pistons and the air tank, which we will explain later on in the slides.
So for our weapon, we decided to go with a pneumatic system versus an electric linear actuator. A pneumatic system can give us much more force output. For our system, we looked at the minimum force required to move the opponent, the output force of our pistons, as well as the number of actuations we'll get on a single tank of air. For our system, we needed a pneumatic piston, an air tank, a check valve, a solenoid valve, a pressure regulator, and the tubing and fittings to connect them. This is the layout of our system. So we included a check valve so we could easily refill our system without removing the air tank. The air tank will be pressurized to about 200 psi. The air will go through the pressure regulator, which will drop it to about 120 psi. The solenoid valve will be controlled by the receiver. When the solenoid valve activates, it will allow air to go into the pistons, which will extend the pistons. Whenever the solenoid valve deactivates, the air will exhaust back through the solenoid valve. Our pistons will be single acting, so the spring will retract our pistons. For the minimum force to move the opponent, we looked at the friction force. We expect the opponent to be 30 pounds, and we use a coefficient of friction of 0.8, a static coefficient of friction. That's the coefficient of friction between rubber and cardboard. It's also close to the one between rubber and wood, which will be about what the combat surface is. For our output force, we took the pressure times the area of the cylinder minus the spring force. So when our piston actuates, it'll be resisting that spring force. The spring force is pretty small compared to our output pressure. We wanted to do this because we wanted to conserve air, only having to actuate one way using our air supply. This is some of the expected forces at various pressures. The top line in bold is the PSI values, and on the left side is the bore size. The bore size corresponds to the diameter of the piston. So our force is only relevant if we can get a certain number of actuations. So for our actuations, we use conservation of mass. We looked at the initial mass in the tank based on our volume of the tank and the density of air at 200 psi. And then the mass change will be the amount of air used in one actuation at 120 psi. So we wanted to calculate the number of actuations for our design output pressure and our output force. So once the pressure in the tank drops below that That's our number of actuations at our design force. And this is the number of actuations for a 4-inch stroke. We also considered a 3-inch and 5-inch stroke, but we decided to go with the 4-inch stroke. We looked at having over 8 actuations. Each match is 2 to 3 rounds. So we wanted to have at least 2 actuations per round, plus another 1 or 2 just in case. So we eliminated bore sizes over 7/8 based on the number of actuations, and also we aren't battling in an arena, so we don't want the forces to get too high and have any shrapnel or anything flying off the robots. So this is our piston. It's an SMC piston. We decided on a 3/4 inch bore size and a 4-inch stroke. It's single acting with a spring return, again to save air. The reason we chose the SMC one is it's double end mounted. Some of the other pistons we were looking at this size are only front end mounted, and we felt that the double end mounted would help keep it aligned and also give it more strength. This piston has a steel rod versus an aluminum rod, so that'll help it resist bending. As far as air tanks, the selection of air tanks at the pressure we wanted to achieve was not very good at this size. We found that a paintball tank would best fit our application. It has a rated pressure way higher than what we're planning on operating at. It's also very small and lightweight, so it won't make our robot bulky. For our solenoid valve, we needed a 3-way solenoid valve with an input, an output, and then an exhaust port. It's spring return, so whenever it deactivates, the spring will return it to its normal position. It requires 12 volts DC, so we actually have another battery just to power this. And it's rated at 145 PSI. Our pressure regulator will drop the pressure below 140, so it'll be safely under the rated pressure. For our pressure regulator, we went with an Ingersoll Rand pressure regulator. They're well known for their compressed air products. It's rated up to 250 PSI, so all our calculations are based on 200 PSI in the tank. So we can actually go higher than that and get more actuations if we want to. And then it drops it down anywhere between 0 and 140 PSI. So that gives us a good range that we can vary the force and maybe get more actuations by lowering the force.
When choosing our drivetrain, we looked at a few different types. The last 4 listed on this decision matrix all have an omnidirectional component to their movement. Especially like the omnidirectional wheels and the mechanism wheels, those wheels themselves just intrinsically can move in any direction that you ask them to. But we decided that as a team, we prefer durability, something low to the ground, and something with high traction over those increased maneuverability. And so that left us with a 6-wheel drive tank or the traditional traction wheels, which is just a wheel with rubber mounted on the circumference. And the 6-wheel drive tank did win, but not by a whole lot, you can see. And so we will talk further about that in just a moment. But we decided that on a dual drive motor system with 2 motors powering the rear sprockets. So these are the main components of our drivetrain system that we have analyzed and selected, and that's the tracks, the sprockets, the motor, the gearbox, and the motor controller. So these are our tracks that we selected. This is a Lynx Motion modular track system, so it's very easy to put together. You just put the links together as many as you want by hand. And that made it to where we had calculated the length of the track that we wanted on each side. And this system made it to where we could get very close to the length we wanted, and we probably will not need a tensioner, but it won't be hard to add one should we need it. So the only issue with those tracks is that the manufacturer provided very little information to us on them. They didn't seem to know what kind of rubber they used on the tracks, and they knew very little about any kind of friction that the tracks provided, which we thought was kind of important for any kind of tank treads. But anyways, we decided that to prove to ourselves that these tracks really would be better than traditional traction wheels, we needed to test for the coefficients of friction ourselves. And that's pretty easy to do. It's physics 1 stuff. You just put it on an incline and do a couple little runs, and that can give you kind of a static and kinetic coefficients of friction. But we had to order the parts, so we did. We got them. They came in yesterday afternoon. So the data was not added to the PowerPoint, but we did some preliminary tests yesterday, and it does appear that these are going to work better than the traditional traction wheels. We took some of those traction wheels from last year's senior design 30-pound combat robots that were up in the E-Lab, and we tested it against those. And it looks like these are giving us a coefficient of friction, a static coefficient of friction of about 0.48, which is about what we would expect from something like this on a wooden surface like that of the stage we will be competing on. The sprockets we chose intentionally to be very compatible with this track because it's made by the same manufacturer for this track. You're going to have 3 on each side, and they come with a 6mm hub, and we couldn't order them without it, even though that's not of much use to us. So we're going to have to replace it with a hub of our choosing to match the drive, the gearbox that we've chosen.
So this is the motor analysis of the motor that we selected, which is the RS755. On the right, you'll see the characteristic curves of the motor. The top red circle indicates the maximum efficiency, which is at which the electrical energy is converted to mechanical energy, for that to maximize. And at the bottom, you see that the torque is around 10 grams centimeters. Two notable specifications on the left side is the rated RPM and the rated torque. The rated torque is around 10 ounce inch, and the rated RPM is around 6,000, which correlates to 119.2 feet per second, which is too fast and way above the linear velocity that we wanted. Also, the stall current's around 44 amps, and we had to keep that in mind when designing and selecting a speed controller. This is the decision matrix for our motor. It was based off of size, cost, weight, and the two specifications that were stated in the last slide. This is our gearbox analysis. The plots on the right are torque and RPM as a function of the gear ratios as they increase. And we noticed that at a 16:1 gear ratio, we got a rated torque of 160.87 ounce inch and a rated RPM of 380. And that corresponded to a linear velocity of 7.45 feet per second, which is right around where we wanted it to be. We also considered a 38:1 gear ratio, which decreased the velocity around 314 feet per second, or 3.14. And it increased the torque to 382.06 ounce inch. This was a consideration, but we figured that it would be too slow, and our opponents would be able to take advantage of that. This is the decision matrix. It was based off of size, cost, motor compatibility, battery compatibility, voltage and current capacity or power capacity, reverse capability, and braking capability. And we decided on the Sabertooth 60 amp regenerative motor driver. This is an image of the motor controller we selected. Has nominal voltage 6 volts to 30 volts, continuous current of 60 amps, which we note is more than the stall current of the motor, which was around 44 amps, which is good because if our motor locks up, we want the speed controller to be able to handle the maximum amount of current the motor will be drawing. We have a peak current of 120 amps and a battery eliminator circuit to power the receiver. And this is the thermal analysis given by the user manual. On the left side, we see a 12-gauge wire size of a 98.63 Fahrenheit temperature. And on the right side, we see an 8-gauge wire of around 86 degrees Fahrenheit. We selected the 8-gauge because it was around 86 degrees Fahrenheit, which is low, and the lower the temperature, the better.
This is the decision matrix for the transmitter and receiver. We looked at 6 different transmitters, some includes receivers and some don't. We decided to select the Fitavis 6J because of its fail-safe capability to ensure we can safely turn off the robot remotely. This is a picture of the transmitter and receiver. It operates on the 2.4 gigahertz frequency spectrum to ensure a clean connection between the transmitter and the receiver and limited interference from other radio signals.
This is the decision matrix for